Okay, today is October 21st, 2021, and there was a change to the syllabus, to the schedule of the classes. I uploaded that to the shareable folder. Double check the syllabus, okay? I changed the date of the second exam. So we now have 1 week and a half buffer between now and the second exam. The second exam is going to be on Thursday. On Tuesday. It's going to be on Tuesday, a week and a half from now. Okay, so from the definition, so let's go back to what we did. We had our little holiday, right? On Tuesday. And so we are talking about the dot product. And what's the starting point? The starting point of the dot product. The starting point of the dot product is its definition. That's where everything starts for the dot product definition. Going back here. That is the, let's see here. Here you go. That's the definition of the dot product. Okay? Go. So can you come by? Let's see. Is four. Let me see. That's okay. Barbara. No, that's okay. That's okay. You can do that now. She wants to make an announcement. Okay, Barbara wants to make an announcement.
Here at Harbor, we're trying to really encourage people to study STEM, and so congratulations on being in physics. This is great. And one of the things we do is we try to keep up with you after you graduate. When you leave Harbor, we like to help you apply to colleges that you think of, try to think about your future. So next week at this time, unfortunately, we're in class, but you can pass this around. You can take a picture if you'd like. These are two alumni that we're going to have at this time next week at 5 to 6. And again, I know you're in class. I don't think you want to take up class time. But it's kind of the reason I bring them up is because of the success they're having. Both of them graduated from Harbor and went on to transfer to USC. Alex, he transferred as an electrical.
Back here. So the starting point. What's the starting point? The starting point is the definition of. Just a quick summary, right? Because you may have maybe a little bit rusty from this little holiday that we had, right? So that's the starting point for the dot product. You know, if you have this definition, everything else follows from it. From the above definition, everything else follows above definition of the dot product. Everything else follows. That's all you have to remember. Okay? So what does it follow? First thing, you know, what this definition tells you? This definition tells you that vectors that are perpendicular to one another has a dot product, right? A dot product of what? Dot product of what? 0, right? Now, knowing that, what's going to happen? Knowing that, you can decompose your vectors into components and get the relations that we got before, right? So what is that? Here you go. This one right in here. That's just one of them, right? Here you go. Keep that in mind. That's work and energy right here. So that's the definition of work, which can be written down in terms of the dot product. Right, and we can now look into what we're going to look first. Here's the genetic equation for the work in 3 dimensions. Okay? Here's the genetic equation in 3 dimensions for the work. But basically what we're going to do most of the time is going to be just to use the equation in 1 dimension. Most of the time, not all. Most of the time, okay? So here we go. Where did we start? P37 note. Okay, here we go. Right in here. Yeah, that's the one I wrote down for you, right? Okay. Most of the time, we will let's see here. Here you go. Let me write it down. For it, there's a 3D force, a 3-dimensional force. 3-dimensional force. The work of not for a 3-dimensional force, but for a 3-dimensional displacement. The work of a given force can, given genetic force, given of the work of a given genetic force can be written as, we go like that, something like that, right? Oh, we're running out of. Bear with me. I'm gonna get the power here to this guy. That's the I gotta take out this step, okay? That's how we write the genetic definition of work. And it can be broken down into displacements along the x, y, and z axis. Okay? But most of the time, but most of the time, we will deal only with one-dimensional forces. Okay? One-dimensional forces. One-dimensional forces is slash displacement. It's dependent not just of the displacement, but dependent on the force as well. You can have a two-dimensional displacement, but just a one-dimensional force. Okay? So here we go for one-dimensional force. All you have to worry about is the integral of the component of the force along the x direction, dx. Okay, like that. Let's come up with let's go ahead and let us go ahead with an example. Here you go. Let's go ahead with this example right in here. Hooke's law, the example of the Hooke's law. With an example of Hooke's law. Hooke's law, how does it look like? Hooke's law looks like the following. Okay. A very important law. You folks are going to work with that over and over again. And I'm going to do that just a one-dimensional case. I'm going to write down as a vector. Like that. Has a minus sign here. Let's go ahead with an example of Hooke's law. 1D. Okay. So what's going to be the work done? Yes.
So does Hooke's law only apply for 1D?
To apply to what?
Only apply for 1D, or is there 2D and 3D versions?
Oh yeah. There are 2D and 3D versions. Yes. Yeah, the Hooke's law, a very good example of Hooke's law is the force of a spring. Okay, the force of a spring, and you can have like three springs attached to an object, right? One along the x-axis, another along the z-axis, and another one along the the y-axis. So the net force is going to be a Hooke's law in the three-axis. Okay, so you can have it, yeah. Okay. But that's very important, Hooke's law, because it applies not just to a spring, but applies also to many other situations out there that we find in physics. Okay? But we start with the spring that is easily seen by you all, right? That, let me see if I have an illustration here. Or Hooke's law, PowerPoint. So the idea of this course, remember, is first to introduce you to simpler situations so you can generalize it later on. So we have this one right in here. Let's see, okay. Where? Hopefully I have one of those examples here. I don't have the circular motion, work, weight, go, genetic. Yeah, here you go. That's the one. Let's take a look at the Hooke's law. Right, this mass is sitting at the position of equilibrium. Right now, the spring is not applying any force whatsoever for the mass. The spring is not stretched, neither compressed. So an ideal spring, the force of an ideal spring, is given by that mass. Okay, the K constant that you saw there in the equation is specifically applicable to what we call the strength of the spring. The harder the spring is, the greater the K is. Okay? That's how you should look at that. Let's write that down there. Here you go. K, the parameter K is the spring constant in Newton per meter with a unit Newton per meter. The stronger the spring is, the larger the K. Okay. The weaker, similarly, the weaker the spring, the weaker means the easier it is to stretch or compress the spring, okay? The lower the K. Okay, that's how you have to. Every object behaves like a spring, even the surface of this table. Okay, the surface of this table right now behaves like a spring. If I'm going to strike the surface of this table, at the very microscopic level that you cannot even see, the surface starts to oscillate back and forth. Can you picture that? That's exactly what's happening when I strike the surface of the spring. But because the surface of the table is so hard, it's so hard, it requires a very large force to make you see it oscillating. Okay? And because the surface of this table is so hard, the K constant of this surface is going to be very large too. Okay? In the case of a rubber band, the K of the rubber band is going to be very low because it can be stretched rather easily. And if you stretch a rubber band, put a mass at the tip of the rubber band, stretch it and release it, that's going to oscillate, right? That's going to oscillate. Okay, so let's going back here. Here you go. Let's illustrate. If you forget how this force of Hooke's law behaves, just do this drawing right here. Okay. I'm going to apply a force to stretch the spring while the mass displaces with it. That's what I'm doing right now. See that? I displace the mass out of the equilibrium position, and I have my hand here pulling the mass to the right. I didn't draw that. Okay? The spring is applying a force to the left. Okay? And the same thing can happen, the opposite thing can happen when I compress the spring. Do you see why you have the negative sign there in the equation? See if you can understand why you have the negative sign there of the equation. In the equation. Here you go, I'm moving the mass to the right, the force is to the left. See? That's where the negative comes from. I displace the mass to the left, the force is to the right. Makes sense now why you have that negative sign there? The negative tells you the direction of the force with respect to the vector x, with respect to the vector displacement from the equilibrium position. That's what negative is all about. Let's see if we have something else. Yeah. Oh yeah, here you go. Now let's play a little movie, right? I compress the spring, release the mass, and then what's going to happen? The speed of the mass is going to build up little by little. It's going to pass through the position of equilibrium with maximum speed. I'm assuming that there is no friction there. Okay? And then, it's going to overshoot this maximum position. It's going to reach the other side of the x-axis around here, more or less, and it's going to come to an instantaneous rest, and then it's going to move back again. It's going to keep on oscillating back and forth. Can you picture that? In the case that there is no friction. This type of motion is studied in Physics 39. This type of motion, here we go. So here we go. Here, that's how the force. Now I'm plotting the magnitude of the force against x, okay? That's how the force changes with position. It goes in a linear fashion, in a linear sense. Let's see if I have something different in the other. Here you go. P37. Yeah, it doesn't look like I have a better drawings there. Yeah, okay, yeah, I don't have better drawings there. But why did I draw that graph for you? Okay, I'm plotting here the magnitude of the force. Let's emphasize that it is the magnitude of the force of the Hooke's law. It's a straight line, right? With a slope of k. I'm going to remove all that stuff that you see here, so you can see the graph alone. You can see the variation. There you go. Increases linearly. If we look at the definition of work, don't forget this F is in reality, right? It's not just the regular F, but it's the F sub x, right? I'm not gonna put it in there because it's gonna mess up with my graph, okay? So if you go in this specific situation, the force is not constant. The force is not uniform. The force is non-uniform. Okay? Because the force is non-uniform, the work done by the force is going to be the area below this graph. Okay? The area below this line. If you're working with numerical methods, you treat this area as small, rectangles, or very thin rectangles. If you're doing, in numerical fashion, and then you calculate the area of each rectangle to find out what's going to be the work done by this force. Okay, here you go. That the area below this curve is going to be the work done by this force. Make sense? We can go back there to the equation, right? Notes. Here you go. That's the work done by the force F. Is the integral from x naught to f of fx dx. Right? So if this guy here is the force, the work done by this force is the area under the curve. Okay? In the case of the weight, here you go, how the weight looked like. The weight looked just like that, right? It's a constant, mg. So the force was constant. I'm going to put here y, because we usually work with y, right? For the weight, equal to mg. It's equal to mg. And the work done by the mg, just like before, is going to be the area under this curve. Go. That's another way of looking at it. It's no different from the definition or the formula for that we did for a constant force. Go. That would be the area, the work done by the weight. And here would be the work done by the force kx. Okay, let's get the work done by the force kx in a formula, in a mathematical format. Here we go. That's the equation we have here. We are going from initial position to a final position. The initial position can be the point of equilibrium, which we define as being 0. But let's keep it as though as it is, right? X naught in the most generic format. Here you go, f sub x I have to take out my here you go. Take out my arrow there. I'm gonna put that between parentheses to emphasize that the force was fit k minus kx was fit within f sub x, and we are going to take minus k from inside the integral. Okay, x dx. And you know how to solve this integral, right? The line integral is just a regular, this line integral ends up being just as any regular integral that you are familiar with, right? What you saw as a line integral before is nothing more, nothing less than a regular integral. The notation of the line integral is just a convenient way of writing down something that's too big. Something that's big. Here you go. X squared over 2. And we are going to apply the limits single brackets. We go apply the limit from the initial position, which can be the equilibrium position. The equilibrium position is usually stated as being x equal to 0. I'm going to take advantage of this guy here, place it right in here, and this guy here. Right in here. And then what we have xf square minus x naught square x naught square. Okay, like that. We have this negative sign in there. There's a reason why we have this negative sign there. Okay, so let's see, special case. Let's look at the special case. Come on, man. Okay. Special case. Yeah, man, this computer is so slow. Special case. Just not supposed to be that slow. Initial position is equal to 0. Initial position is equal to 0. Okay. So what's happening? In this case, for this special case, the work done is going to be what? It's going to be negative, right? Because xf squared is going to be positive no matter whether xf is negative or positive. The square of any number, any real number, is always positive. Okay? So let's take a look at the drawing that you saw before. Right in here. So we were... Not this one. Nope, not this one I want. Maybe I can use this one. Okay, not this one. Let's get the other one. Okay, let's see here. Okay, here you go. Let's say I'm initially at the initial position, x not equal to 0. And what I'm going to do first, I'm going to extend the spring with my own hand. Okay, I'm gonna get that block in there and stretch the spring. My hand is going to do some work. Okay, and the spring is going to resist my work. Make sense? My hand is pulling the spring to the right, and I can even put, this vector force here of my hand right in here, pointing to the right. Those two forces are different because one is from the spring, the other is from my hand. My hand is going to do positive work because it's in the same direction as the displacement vector. Here you go. And I'm gonna label it my hand. Force of the hand. And I'm gonna put H to denote it's my hand. Here. The force should be a little bit better, right? My hand is doing positive work on this mass. But in the process, the spring is resisting my work. What does it mean? It means that the spring is doing negative work. Can you picture that? That's why I got a negative value there for the work. That's why I got a negative value for the work. So it depends on the initial conditions, right? The initial conditions was this one right in here. And went in there. Okay. Another case, right? I can P37 notes. I can start at no matter it's to the right, no matter it's to the left, right? It doesn't matter if it's positive or negative. Here you go. The work is still going to be negative. Here you go. You start here, end up here, final position again. I am compressing the spring. My hand is doing positive work, but the spring is doing negative work. It's resisting the motion. Okay? Just like the frictional force. But the weight and the norm are going to do zero work on this guy. Okay, that's what we have here. 5:45 already. Okay. So let's see. Yeah, let me take attendance, right? Let me see. Before I take attendance, let me see what else is coming. I'm not tired yet. I see we can keep on going. Here we go. Yep. Negative. Okay, what would be an example of positive work done by the spring? That would be an example of positive work done by the spring. The spring can do positive work, yeah, the spring can. Okay, so what would that be? Here you go, I'm gonna show an illustration. Here you go. We have now this position here as being the initial position. It's just a matter of what you call the initial position. It's just a matter of what you call the initial position. And here we have the final position. Okay, I release the mass is initially at rest, at this position. I release this mass, right? And then what's going to happen? It's going to move from this position, from this initial position, to the final position here. Hmm. One more position. Oh yeah, here you go. Here's what I want. See that? Yeah, that was the original initial position, right? We can we can define the initial position as being something else other than the origin. Now the spring is doing some positive work. Okay? And I'm going to go right in here. I'm going to put this guy at this point. And this X too is going to go there. Playing the movie for you. Positive work done by the spring. You can have positive work done by the spring. Okay? Positive work done by spring. Let's see. Here you go. Notes. Positive work. Positive work done by the spring. Okay? Initial position with the spring either stretched or compressed. With the spring either stretched or compressed. Final position 0. Okay, so here you go. Just use the same equation, the same genetic equation that we did before. Work done. Okay. Final position is 0. Final position is 0. Initial position is non-zero. This negative cancel out with this negative. Okay. Like that. Okay, so 5:48. Let's go ahead and let's take attendance. And I'm going to stop the recording. Remind me when you return from the break. Okay, again, we're going to do some derivations, a little bit lengthy, but it's an important derivation. We call it the work-kinetic energy theorem. The key word here is theorem. It's not law, okay? Law is different from a theorem. So a theorem is a consequence of something else. A theorem is consequence of a law in conjunction with a definition. This specific theorem is a consequence of a definition, the definition of work, in conjunction with Newton's law, Newton's second law of motion. Okay, and it's called kinetic energy and work. Kinetic energy. Either wait a minute. It's called work kinetic energy theorem. That's what it's called. So let's do this definition, and that's gonna be the theorem that we're going to use for the rest of this chapter, chapter 7 and 8. That's why it's so important. Okay, the remaining of chapter 7 and 8, we are going to be use this theorem, and what I want. That's why I want you to understand this derivation. Here you go. Work kinetic energy theorem. Work kinetic energy theorem. Okay. Okay. This theorem is a consequence of two things. One, the definition of work, and Newton's second law of motion. Putting those two things together, we can come up with the theorem. Okay, and by the way, it is this theorem that gives rise to what people call the law of conservation of energy. That's what this is all about. Okay, let's write that down here, right? This theorem is what people call incorrectly, okay? The result, the application, you go, the application, one of the applications, let's put it this way, one of the applications of this theorem is what people incorrectly, even books call that, incorrectly call the law of conservation of energy. The law of conservation of energy. It's not a law, it's a theorem. It's the WorkKineticEneryTheorem. If there is any law of conservation of energy, it's not in mechanics. The law of conservation of energy that we have is in thermodynamics. Okay? So that's very important to organize your heads about that. It's unfortunate that, books, they don't clarify that to us. It's unfortunate. And so let's see. One of the what is the okay? So how this theorem? And remember, it's a theorem. It's not a law. Okay, laws are far more important than theorems, right? Laws are the kernel of everything. A theorem is a consequence of that kernel. It's a consequence of that building block. It's the consequence of that core. Okay, so how do we go for that? How do we go? Okay, this theorem is obtained. How do we obtain this theorem? By starting with the work done by the net force. Remember that I told you the work can be the work of a force. The work of a force can be the work of any force. Can be the weight, can be the normal, the work of the force of friction, can be the work of the net force. The work of the sum of a set of forces, not necessarily the net force. That's what work can be of any type of force. And then there is this important force, which is the net force, that when you take the work done by the net force, you get this important theorem. The theorem, the work-kinetic energy theorem. So how do we do that? Let's go ahead and let's define what we're going to do for one-dimensional first, and then we're going to do three-dimensional afterwards, okay? Let's start with one-dimensional first. Let's start, let us start with the 1D case first, one-dimensional case. Then we will extend to the 3D case. It's possible to extend to the 3D case rather easily, but it's a little bit more mathematically involved. But let's start with the 1D case so you can understand that better. And then once we have a grasp of the 1D case, we can move on to the more difficult one, right? It's not that it's more difficult, it's just like more mass intensive, more work. Okay, that's the difference between something being difficult and something being mass intensive, something that requires lots of work. There are many things out there that require lots of work, but it's easy to do, right? Provided you hire a bunch of people to do that work for you in a small amount of time, right? And then there are problems that are very difficult to do, that you can have a single individual to solve it. Okay. Okay, so let's start with the definition. The definition of the force, right? I'm gonna remember, and it's a special case of, it's a special type of force. It's the net force. So I'm gonna write that down. Work of the net force. Work of the net force is going to be what? It's going to be the net force. We are doing just the one-dimensional case. And because we are doing just the one-dimensional case, dot dx, right? And what's going to have next? Remember that I told you this is the result of two things. This is the result of the work of a net force and Newton's second law of motion. Okay, so let's go ahead and apply Newton's second law of motion. Newton's second law of motion states that the net force is equal to mass times acceleration. Make sense? Everything's there inside the integrand. And it doesn't matter which type of acceleration I'm talking about, folks. Doesn't matter. Can be any type of acceleration. Can be zero acceleration, can be constant acceleration, can be even accelerations that are not constant. And you're going to understand why. That was so neat about this theorem. Okay? See, I'm not making any assumptions about the acceleration here. So much that I'm going to rewrite that in terms of dv dt. There's a reason why I do that. This is a mathematical trick. Most likely this was a very difficult problem, and someone some time ago had this flash of genius and came up with this realization that the acceleration, not only the acceleration can be written down as dv dt, but also they could do something else to solve this integral equation. Okay, one of those amazing results. Like I told you, it was very difficult to find that way, that simple solution. It was very difficult. But once you found it, it becomes very easy to solve it. Okay, it was not lots of work. Okay, but it was very difficult to find the solution. What's the next step? Okay, the next step, the genius realization, was that we can commute the dt here with from the dv to the dx. Okay, such a simple solution. So instead of having dv dt, and we can do that because this is a well-behaved function, right? Like any physical functions are. Here you go. Now I can, just by coming out with this realization, it becomes very easy to solve this integral no matter what the type of acceleration is all about. I'm still integrating on x naught, but what happens? Now I change it. I still put in the limit in x naught to xf, right? But then what did I do? I changed my integrating variable from the x to dv, right? See that? The moment that I change my integrating variable from the x to dv, I have to change my limits of integration as well. Instead of initial position, now it's going to be initial velocity. Instead of final position, it's going to be now final velocity. Okay? And then we're going to go for the next step. The next step is just making the equation looks nicer. But wait a minute. You must realize that dx dt is in reality v, right? And now let's make it look nicer just by commuting those two elements of the integrand. So we put the integral in the regular format. Do you know how to solve this integral? Do you know how to? Oh, well, there's one more thing you gotta do, right? The mass is constant. I'm assuming that the mass is constant. Under the assumption that the mass is constant. Okay, here you go. I should have put the mass outside the integrand since the very beginning, right? Here you go. Let's do that here. Here you go. because the mass is constant. Here you go. Put it here, put it here, and put it here. Oh, and put it here. Here you go. Now we're going to solve this integral. It's going to be v squared divided by 2. I gotta put the v squared here. Oh, what did I do? Yeah, that's fine. No problema here. And I'm gonna put the limits of integration as well. That's the one. Let's go down. That's not the one I want. You want this one? No, we want this one here. Yeah. And we apply the limits. I'm going to change the name of my integrating variable. Instead of calling it, here you go, v naught is going to stay as v naught. What I'm going to change is the final velocity. Instead of calling vf, I'm going to just call v only v. Okay? That's we are almost done with the one-dimensional case of the work kinetic energy. It's just a matter of applying the limits. Here we go. V squared. We apply the limit of v squared, we leave this way. And now let the other limit, here we go. We're going to v naught square. Here you go. And now I'm going to write it down. I'm going to break it down. Let's see how I'm going to do it. Yeah, let me break it down. Books usually do that. Mv squared minus half v naught square. Oh, don't forget the m, right? Mv naught square. Here you go. That's the work-kinetic energy theorem. Okay, because this term that you see here shows up so frequently, half mv squared, we call it some type of energy. We call it the kinetic energy. Okay? The two terms on the right side, the two terms on the right side are defined as the kinetic energy. Okay, here you go. That's why we call it work-kinetic energy theorem. Okay. Kinetic energy, whereas kinetic energy is defined as energy due to motion. Okay. There's another type of energy, but let's stick to this one first. Energy due to the motion is kinetic energy, half mv squared. So that's where this definition comes from. This definition comes from the work-kinetic energy theorem. Now that's one-dimensional case. Let us do the 3D case. The 3D case. It's a little bit tricky, but again requires some knowledge of physics. Remember, it's always the net force, right? So, but now the net force is going to be a vector. And don't forget that the work is always always defined in terms of a dot product. Go. You go in the dot product would be go. Go F net dot dr. You go dr here, right in here. But I gotta put the dot there now. It's a little bit more mathematically challenging, but it can be done. We know how to do it. It doesn't require a special discovery. Where's my dot? My dot product, where is it? Oh, right in here. Here you go. Dot, oh, wrong place. Here you go. Here you go. But now, because we're integrating in this position, in the position vector, right, we have, let me see, I'm going to use this one here. We have to apply the limits in terms of a vector. The limits doesn't have to be necessarily a scalar. The limit can be a vector as well. The initial limit is R0. And the other upper limit is final position. Like that. Makes sense? We're integrating on the position vector. Consequently, we have to apply limits in terms of the position vector. Just like we did for the one-dimensional case, the net force is also the mass times acceleration. But it's the acceleration that is a vectorial acceleration. Let's see, I'm going to do it like that. And an integrating term, that's also a vector, a dot product between vectors. Here you go. And I'm going to put it an A here. Like that. In the next step, we just do the same thing that we did before. We take the, oh, don't forget to to get the vectors there, right? R0 to RF. And now I'm going to start just copying what I have here so I don't have to be dealing with vector signs. Here you go. Come on, man. Yep, here you go. First thing we do is to take the mass out of the integrand. Next thing we do is to replace the A with a dvdt vector. Dvdt vector. Here you go. Now I don't need this guy anymore, right? Next step. What do we do next step? If you remember what we did before, just refer to the one-dimensional case that's right in here. What do we do with the dt term? We commute it, right? I'm just gonna copy this one. Oh, I feel that takes so long to do those things. And just change the v vector to r vector. If you're doing that by hand, it would be far quicker, right? And but of course, it wouldn't be as nice. Oh, we still have a dot product there. We still have a dot product, and like it happened before, we have to change the limits now. That we change the integrating term, the integrating parameter, change from R to V. And then we make it look nicer by commuting the two vectors. So it looks nicer. Here we go. I'm gonna commute that here with this one. Remember, it's a dot product, so we can commute the terms. Go. Like that. And then, what else? What's the next magic here? We have, it's gonna be a little bit different because we have that dot product that I didn't resolve. If you want, you can break down this dot product, okay, in x, y, and z components. You can, if you want, you can do that. But then you're gonna get a huge line there. So here we go. Here you go. Okay, that's what we get, right? And you still get the same result because what you have here can be rewritten. I'm going to erase that for now. No, leave it there for now. Leave it there because you can save me something. What you have right in here, you'd be able to recognize that what you have right in here is what can be rewritten in terms of a total derivative. Okay, and the total derivative looks just like that. V dot V. We apply the chain rule. Okay, you get V dot dV plus V dot dV. So in reality, we have to put a half here. Okay, and now we are changing our integrating term again. Let's go ahead and copy here and paste it here. Now I don't need this guy anymore. Okay, and I can replace that V dot dV with this total derivative term. Okay. Since we have now a total derivative term, we have to change again the integration here, right? The integrating terms, I'm gonna put V naught dot V naught here, VF dot VF here. Makes sense? Since we But then I'm gonna do something else that's gonna make it look even more clear than before. V dot V is what? What is V dot V? When you take the dot product between the same vectors, we can represent them how? What's the new?
Just the scalar quantity
Yeah, just like but the scalar quantity of which quantity?
of the magnitude of the vector.
Just the magnitude of the vector? Just the magnitude of the vector? Think about that.
Yeah, pretty much.
Here you go. Is this what you see here is the magnitude of the vector? Or is it the magnitude of the square of the vector? Right?
The magnitude of the square.
Square of the vector. Yeah. Good. So here you go. So next, I'm gonna factor out this half term here. Okay, and I'm going to call this one, a scalar. Okay, a square, right? A scalar. The square of the scalar velocity. And now that I change it to the square of the scalar velocity, I also have to change here to the square of the initial velocity and the square of the final velocity. Yeah, here you go, like that. And now you know that this the integral of the v square is what? V square, right? The integral of the v square is v square. And we apply the limits here. But let's not forget that now, I'm going to emphasize that what you have here, you know, my new variable is no longer v. I'm going to emphasize it here. My new variable is v dot v. Here you go. Oops. See that? V dot v goes from v naught dot v naught to vf dot vf, right? And here's the same thing. That's my new variable. All right, and then I go ahead and copy this one. Here you go. So what was a vector, an integral of a vector became the integral of a scalar. Nice, isn't that? And I don't even need the parent. Leave the parentheses there, right? Leave the parentheses there. And I'm going to emphasize that we must substitute v square with v naught square. Okay, that's what I'm emphasizing here. That's what I'm emphasizing here. Otherwise, if I replace v with v naught squared, it becomes v naught to the fourth power, right? So I gotta emphasize that. And finally, finally we get what we got before. But let's not forget now that what you have, Again, I'm going to rename VF with a Z, right? Let me rename VF with V so I don't have that mess there. Oh, by the way, it's not V, it's V square. Oh yeah, I already have V square here. Here you go. Simplify the notation. The only difference now is that this V, where I'm gonna emphasize here, where V square is what? What time is that? 6:42, almost there. 8 minutes to go. Is equal to V. I'm gonna take advantage of this guy. This is a three-dimensional situation, right? Vx squared plus Vy squared plus Vz squared plus Vz squared. And the same thing for V naught. It's a three-dimensional velocity. Same format, just like before, we call that the kinetic energy. Just like before, we call the above term the kinetic energy. And by the way, I didn't do in the previous one. Okay, let's do that here. I didn't do that. Yeah, I didn't finish here. Just one small step here. Okay, work of the net force is equal to what? Is the final kinetic energy final kinetic energy minus the initial kinetic energy. Okay. Can you remember that easily? It's a simple result, right? That's the work kinetic energy is all about. The work of the net force is just the difference between the final kinetic energy and the initial kinetic energy. The format has the same, looks the same, right? But the velocities are different. The velocities are, whether it's in one dimension or three dimension, the velocities are sort of different. Okay, so that's what this thing here is going to propagate. That's what this result that we're going to keep on using for the rest of the remaining of chapter 7 and chapter 8 and beginning of. Let me see if I have anything else here. Oh yeah, see, I did the different. I did the derivation now by expanding the dot product, right? It's a far more. See that I spelled out f dot dr with fnet in the x direction dx plus fnet in the y direction dy, blah blah blah. Right? I didn't do that here, but in the previous one. But that's the way we do it. There's another way we can do to prove the same thing. I didn't want to do this way because it would be too many integrals for you to. But if you want to look over that, we should get the same result. Work-kinetic energy theorem. We'll use throughout this course many times, not just chapter 7 and 8, but also throughout the course, even in physics 38. Okay, even in physics 38. What's going to come next is a new way of classifying the forces. Okay, so there is forces that are contact force and non-contact force, right? Remember the beginning? Then there is also a different way of classifying forces. Instead of contact forces and non-contact forces, we classify them as conservative forces and non-conservative forces. There is a reason for that. And there is a reason for that. Okay? And you do study something like that in math. Okay, and then we go through that. Let me see. Don't go yet. Let's potential energy difference. Let me see here. I think that what you're seeing right now is chapter 8 in the book already. In my notes is chapter 7. Yeah, types of potential energy. Let's see. Let's go. Let's keep on going. Yeah, at this point, I'm quite sure that what you see here is in the book chapter 8. Let me make sure. No. No. Okay, so that must be chapter 7 in the book. Okay, and then chapter 8 is going to be example of the use of work and energy. Okay. So we can stop here now. And any questions about that? We have 2 more minutes to go. We're going to have an experiment there upstairs. I want to